Welcome to the Problems Channel Season 2, Episode 20, the episode which I have titled Fresnel Integrals via Equations, because in this episode we will evaluate the Fresnel integrals over the positive branch of the x-axis using nothing more than the equation problem-solving approach. Before we do that, however, as a traditional friendly reminder, if you are joining our channel mid-season, then first of all, thank you very much for your vote of confidence and welcome to our channel. And second of all, it is a good idea for you to go to the channel's homepage and in the channel's trailer section find the episode titled The Problems Channel How To and watch that episode in its entirety. Follow all the instructions that were given in this episode. That episode is not too long, it's about 20 minutes. But if you want to derive the most of an academic benefit from working with the material presented on this channel, then we suggest that you follow all the instructions that we give in that episode, and that way you will understand what we're doing on this channel and why. In the mathematical problem S2E20, we are asked to evaluate the Fresnel integrals shown here and here over the positive branch of the x-axis using the equation problem-solving approach and knowing pretty much the only thing that we are allowed in some sense to use when it comes to integration, knowing the value of the Euler-Poisson integral shown over here. Before we deep dive into the underlying mathematics of this problem, as an optional extra for experts, here is a 2-minute crash course on the origin of the Fresnel integrals. Cutting the long story short, the Fresnel integrals shown over here in their pure mathematical form, so to speak, originate from the branch of physics called optics, which itself has several branches in it, such as the geometric or ray optics, physical optics, wave optics, molecular optics, and so on. For example, the geometrical or the ray optics is built on top of 4 experimentally discovered laws. One of such laws claims that light propagates over a straight line. However, it was eventually noticed that even in this classical model, in which again we model the propagation of the trajectory of light with a straight line, which is an idealistic geometrical object, sometimes light deviates from this straight line propagation in the presence of mechanical obstacles, such as, for example, fog. When we look at the source of light that is located some distance away from us through the fog, then it seems that the light dissipates or scatters in all sorts of directions. Or when the light travels through an opening in an otherwise completely non-transparent or completely opaque screen. That opening over here is called aperture in physics. And in this case, this observation, in a sense, probes the limitations of the geometrical or ray objects, because when light, for example, passes through such an aperture, then every point on the boundary of that aperture is considered to be a secondary light source. As such, this deviation from the straight line propagation, also in the presence of certain other constraints that are not important for the purposes of this discussion, this phenomenon overall and essentially in that many words is called diffraction. And the phrase "to solve a diffraction problem" means to recover certain parameters of diffraction that unfolds under certain scenario. Again, which parameters over here doesn't really matter or important. I want to keep the size of this video manageable, so we will omit these particular details. But this is exactly where the physical optics comes in as we switch from the geometrical or ray optics. We switch to the physical optics, which basically studies the physical nature and the interaction of light with everything else. And in physical optics, it can be shown that literally every diffraction problem can be treated very formally mathematically, and every such problem can be reduced to a system of the so-called Maxwell equations, or shown over here. I will not be going over the details again. That's not really that important for the purposes of this episode. I want to keep the size of this episode manageable. But the point is, the main takeaway is that each and every diffraction problem can be treated mathematically, absolutely rigorously, and through this mathematically rigorous treatment, such a problem can be reduced to a solution of the Maxwell equations. However, the other side of this coin is that the equations that come out on the other side of such a mathematically rigorous treatment do not admit analytic solutions at all, except or barring for very, very simplified situations. And as it turns out, for the most part, from the practical standpoint, we do not really this absolutely rigorous mathematical treatment in this case. Some approximations are enough. And one of such approximations, along with a certain principle of diffraction, was introduced by the French physicist Fresnel. He lived during the time that is shown over here, and consequently the scenario that he described and studied, and for which he put forward his famous principle, is now known as the Fresnel diffraction. It characteristically takes place when the size of the aperture shown over here is this opening in an otherwise completely opaque and non-transparent screen is way larger than the size of the wavelength of the incoming light. And the so-called diffraction or interference picture, you may have seen it in various textbooks. It looks precisely as a series of concentric circles or rings. And here, consequently, if we throw our favorite orthogonal coordinate system shown over here this way and this way, let's say this is the x-axis, this is the y-axis. When you look at this picture, what first analytic expression that comes to mind when you look at these things? Well, x squared plus y squared, essentially. I'm ignoring, of course, all sorts of gory details, but in the gist, that is what is happening here. So from this expression, a certain magnitude, a certain field in physical optics when it comes to the solution of a particular diffraction problem is expressed as an integral shown over here from 0 to s, and the integrand looks as follows. E, or the base of the natural logarithm, raised to the power I times pi times s squared over 2, and the whole thing is integrated over the dummy variable s over here. And the symbol I is our favorite imaginary unit. It has the property that when it's squared, it yields -1, as shown over here. And I is famously one of two generators of the multiplicative group of fourth roots of unity shown over here. I designated with the U4. You may designate it with something else, but this is basically a finite set of 4 elements, plus minus I, plus minus 1. So all the powers of, let's say, I generate the group, hence I is the generator of the group. And essentially, this is where the Fresnel integrals come from in their pure form, the way they are seen in the physical optics. The integration argument will be clearly what? Pi s squared over 2, but through a transparent and straightforward change in variables, we reduce these integrals to this form shown over here. And now in the next few segments, we will show how these integrals can be evaluated using nothing more than the equation problem solving approach. And as long as we agree that ahead of time, we know the value of the Euler-Poisson integral. The more you do mathematics, the more you will realize that there is more to mathematics than meets the eye, and that overall, and first of all, mathematics is an art of telling a story, an art of telling a story of how and why. If we agree to designate a given mathematical problem with the geometric point, for example, here, and if we agree to represent the answer to such a problem with another geometric point over here, then a solution of a given mathematical problem that leads to this answer can be represented with a curve that somehow meanders, going this way and that way, and then eventually terminates with the answer. This is a problem, and this is the answer, and this is a solution. For example, another solution will meander some other way, but it should terminate at the same point as well. On this channel, what is interesting to us is not as much as the answer, but precisely this path over here, because in order to generate the said story about how and why, we as the authors of this story must exhibit precisely the ingenuity, the creativity, and the improvisational skills, and that is what we're trying to develop and nurture on this channel. Consequently, it is important to understand the proportions between mathematics and not mathematics that we're about to witness in the solution of the problem S2E20. Here, again, it is important to understand that the mathematics, so to speak, in this problem is the process of generating the idea to orchestrate the process of evaluating the Fresnel integrals over the positive branch of the real axis using nothing more than the equation problem solving approach. And everything else that follows is subordinate to that idea, and in some sense either not mathematics that we write with the capital M, or at best lesser mathematics. In other words, using a corporate analogy, the mathematics in this case plays the role of the product manager who decides what needs to be done to begin with. Once that what has been discovered or generated, everything else becomes a motivation for what follows. How do we carry out the what? Consequently, the battle plan for this problem is taken out as a classical playbook of the equation problem solving approach. Introduce as many variables as needed, construct as many equations as possible, balance both the quantity and the quality of these equations against the nature of the problem, solve as many equations as you can, and then validate the results against the specific nature of the problem. This is our plan, and this is how we will execute it. In case you missed it, in Season 2, Episode 16, I'll write it down for you guys over here. In Season 2, Episode 16, in this guy we explain the mechanics of the equation problem solving approach, and according to the equation problem solving approach, if we want to solve this or that technical problem using one or several equations, then the first order of business is to introduce as many variables as needed. Because each and every problem-solving approach is just a heuristic template that does not provide a solid algorithmic guidance. In real time, we do not really know ahead of time how many and what kind of variables will be needed. So here again, in real time, as we try to solve this problem as the way it is framed, we will try several things, we will fail several times, but eventually we will hone on the idea of, let me erase this thing, we will hone on the idea of introducing two variables, two strictly positive real numbers. Let's refer to these guys as A and B, strictly greater than 0. And then once these variables are introduced, we take our Fresnel integrals and we morph them into slightly more generic integrals as follows. We'll introduce, let me use, let's say, green color for the function c of a, b, which will be an integral from 0 to positive infinity of e to the power negative ax squared times the trigonometric function of cosine of b times x squared dx. And in a similar way, I'll use the blue color. Maybe let's write it over here. Introduce the function s of a and b. That will be the integral from 0 to positive infinity e to the power minus ax squared times the trigonometric function of sine of bx squared dx. One more time, just to make sure that we're all on the same page. The function c of a and b is the integral from 0 to positive infinity over the positive branch of the real axis or the positive branch of the x-axis of the integrand. That looks as follows: the base of the natural logarithm e raised to the power negative ax squared times the whole thing is multiplied by the trigonometric function of cosine evaluated at the argument b times x squared, and the whole thing is integrated over x. Likewise, the function sa of b is an integral over the positive branch of the real axis of the base of the natural logarithm e raised to the negative a times x squared power, and the whole thing is multiplied by the trigonometric function of sine that is evaluated at bx squared, and the whole thing is integrated over the dummy variable x. The whole idea of this maneuver is to show then that as the functions of a for function c and as the function of the variable a for the function s of a and b, these functions are continuous, and this can be done. I do not want to spend too much time on proving that if you, for example, are writing an article for a publication or for a review, you will have to go through these motions. Here I'll skip it. I'll just say that according to the real analysis theorem, if we can show that this integral here and here converge with respect to the parameter a uniformly, and it can be shown that they do, then the corresponding functions as functions of the parameter a here and a here will be exactly that, continuous on the appropriate domain. Once that proof is on the books, then we execute the following maneuver. We take the limit of the function c of a and b when what is happening? When a tends to 0 from the right, and then what do we have? Well, precisely through the machinery of real analysis, we will have an integral that runs from 0 to positive infinity of cosine of bx squared dx, and over here we will take the limit of the function, let's see here, s a of b as, again, a tends to 0 from the right. And what do we get? We get the integral from 0 to positive infinity of the trigonometric function of sine of bx squared dx. Once that is understood, we will again obtain the integrals that are pretty much our Fresnel integrals, but here with the value of b set to 1, what will we have? We will have precisely under the, let's say here, under b equals 1 and under b equals 1 setting, what will we have? We will have precisely the integral from 0 to positive infinity of cosine x squared dx, and here we will have the integral from 0 to positive infinity of the trigonometric function of sine of x squared dx. These are precisely our Fresnel integrals whose values we're trying to compute. And here, because I respect your privacy and I will never utter your name in the public setting without your explicit permission, I will say only this, that some members of our community already asked me a very deep and very interesting and meaningful question. Roman, how do you know How do you know when, and how do you know how? For example, how do you know when to give up trying to solve this or that mathematical problem? How do you know what material, what auxiliary objects to introduce into the local material, and how to sprinkle them and mix them with the local material and deduce this or that? That is a very good question. It is interesting to me personally. For a number of years, I was trying to answer the question myself. And unfortunately, the bad news is that I do not have any algorithmic guidance for you guys. The only thing I can say is this. For example, here's a wonderful book. It says Hungarian Problem Book 1. My kids gave it to me for one of my birthdays. That book covers the Hungarian math competitions between years 1894 and 1905. This particular book in English was translated by Elvira Rappaport. The book is absolutely wonderful. In the back over here, there is a short biography of a gentleman who was in charge of all these competitions. He had an immaculate mathematical taste for absolutely wonderful, tasty, and delightful problems. This book and similar books is filled with such delightful problems. So sometimes I would chain myself, let's say, to a desk and try to solve a problem from this specific book. And when I succeed, I go back, look at my records, and I try to understand for my own purposes what was the initial spark that gave the impetus for an idea that was eventually successful and that allowed me to solve this problem. Every time I fail, I do not understand how this happens. The only thing I can tell you guys is that we as humans learn, and maybe with all this AI business, we will learn something else. But so far, we learn following a highly hard scientific doctrine of monkey see, monkey do. In other words, we see how other people do things, and we're trying to figure out how we should do this, and sometimes we succeed. But still, this answer is not very satisfactory even for myself, because it doesn't answer the question. The person who provides the guidance, how does that person, he or she, how does he know how to generate this or that idea? This is still not clear. Using the words of the British mathematician and theoretical physicist Isaac Newton, upon thinking about it, somehow from the depth of our conscience and or maybe unconscious, from the overall web of mathematical knowledge and possibly something else, we yank out the initial idea that then becomes a fruitful step that allows us to solve this or that problem. That much I can tell you guys. So overall, again, in real time, you will act and think in different ways, but eventually one way to solve this problem is to introduce these two extra variables, a and b, strictly positive real numbers, then to wrap our Fresnel integrals into something more generic and more generic as shown here and here, prove that the integrals c of a and b and s of a and b represent functions that are continuous over a by using the uniform convergence of the underlying integrals. Take the limits of both functions when a tends to 0 from the right here and here, obtain slightly less generic integrals that are right in the wheelhouse of the Fresnel integral. Set the parameter b to 1 here, b to 1 there, obtain the value of the Fresnel integrals. And next, as the equation problem solving approach prescribes, we are to construct as many equations as possible with the introduced variables, and then balance not only the quantity but the quality of these equations against the nature of the problem at hand. The second step of the equation problem solving approach prescribes us that once we introduce as many variables as we needed, and here we introduce two such variables, a and b, strictly positive real numbers, we should construct as many equations as possible, and we should balance both the quantity and the quality of the constructed equations against the specific nature of the problem. In that description of the equation problem solving approach, I purposefully designed this perhaps an overkill of constructing as many equations as possible, because on the one hand, in certain situations, it is actually quite difficult to construct as many equations as needed for the resultant system of equations to be solvable to begin with. On the other hand, if we construct too many equations, then more equations than we need to figure out which equations are fruitful in this specific case. In this problem, we can differentiate both of these functions c of a and b and s of a and b apparently over both parameters a and b. Again, if you are writing for publication or for the audience that will that will demand these proofs, you technically need to generate these proofs. You need to put it in black and white. Integrals, you need to show that the integrals converge uniformly over parameter this, parameter that. But here we can again differentiate the functions c of a and b and s of a and b over both parameters a and b. And in real time, it's not initially clear, okay, differentiating these integrals over which parameter and how many times will be fruitful. Again, this is the wonderful part of doing mathematics. We do not know ahead of time what will work. We need to get into the habit of developing our intellectual stamina of saying, okay, try this thing, it didn't work. Okay, we do not give up yet. Try this. Did it work? No. Try that. Did it work? No. Keep trying things until we eventually beat the local material into submission, so to speak, and solve the problem. In real time, you are more than welcome to try different things, but here is one victorious path that definitely works. I tried it obviously ahead of time when I was preparing this episode, and the whole idea of this segment will be to show that the function c of a and b shown over here satisfies this specific equation, even though that again we can differentiate this function with respect to the variable a, still differentiating with respect to the variable b is a winning step. So in order to do that, let us just differentiate the function c of a and b. Let's write it over here. We technically, because we treat these integrals as functions in both a and b, you may argue that, okay, maybe we can integrate, we can differentiate these guys in full differentials. We do not need to use partial derivatives, but I think more pedantically, perhaps partial derivatives here are more appropriate. So the first derivative of this function, c over b, will be, due to the rule put together for us by Leibniz, will be what? It will be the integral of the derivative of this function that contains b. This is essentially we swapping the order of limits. That's why we need uniform convergence in this step, but let's say we did it. So here we have a composite function. We know the first derivative of a composite function is the first derivative of the outer function times the first derivative of the inner function. So here the first derivative of the trigonometric function of cosine is negative sine. So we write down minus integral from 0 to positive infinity. The first derivative of cosine is sine. The first derivative of this expression over here with respect to b will be x squared. So this is exactly what we write. X squared times e to the power negative or minus, let's say, x squared sine of bx squared dx. And right away, also again in real time, it may be not that obvious, but as you solve more and more problems like this, you develop your nose, you develop your intuition for these things. The more such problems you solve correctly and on your own, the better your nose and your intuition becomes. So here right away, we also differentiate this function s of a on b with respect to b once. And what will we have in this case? Well, here d of s over b will be what? Again, we're swapping the order of limits, carrying the differentiation through. The first derivative of the trigonometric function of sine will be the trigonometric function of cosine times the first derivative of the argument with respect to b, which is simply x squared. So here we do not have the change of sign. It's still the same sign, so it will be the integral from 0 to positive infinity of, let's carefully write it down, x squared e to the power minus x ax squared times the trigonometric function of cosine of bx squared dx. So far so good. Do not just trust Roman blindly. Keep Roman honest. Verify that I did not goof off over here. I did not make any mistakes. By the looks of it, we are in good shape. So now, as I promised in the previous episode and at the beginning of this episode, we will not be doing any integration per se, but we will soften these integrals over here in the next couple of segments by applying the integration by parts to these integrals, to these derivatives once. Now, you remember this wonderful formula from whatever course you took, that the integral of u dv is u times v minus integral of v du. This formula applies to indefinite integrals, it applies to Riemann or definite integrals, and it also can be carried through into the world of improper integrals when the proper limits are computed over here. The question is, again, in season 1, episode 2, we explained how to practice mathematics correctly. One way to do so, we suggested that you do not look at our solutions all the way, just try to watch for the minimum viable amount of information until you decide and until you realize, aha, I see what's going on. At that point, put the video on pause, walk away, try to solve the problem on your own, compare your answer to ours. Hopefully you know the spiel. But the thing over here, how would you partition this integrand over here in order to apply integration by parts to it once? Well, here is one way. And carving up the integrands or functions like this into, or partitioning them into different factors is a skill that is good to develop. You will be doing this in the course on complex analysis left and right all the time, all day long. So start learning this skill. So here, one way to do is as follows. We put for the function u, we steal one copy of the dummy variable x and we glue it to the trigonometric function of sine. So then u becomes here x times sine of bx squared. So far so good. Then what does v become in this case? Well, what is the leftover from this partitioning or carving up process? Well, we have one copy of x glued to the exponent. So we will write x times e to the power minus ax squared dx equals dv. That maneuver is understood by everyone in the audience. Very nice. We took the remaining single copy of x that is glued to exponent. The sign is taken by u, and this is became, with the first differential dv, it became this material over here. But now, hopefully, you see what is going on. Here we simply move negative a and x under the first differential over here. And if we do that, what do we need to do? We need to compensate negative 1 over 2a e to the power minus ax squared d what? Negative ax squared. See, this is the manipulation that should be quite straightforward and everyone should understand it. We simply moved this, and this material under the first differential. And if we unwind this step back, what will we have? The first differential of this expression will carry the minus out. This minus and this minus will cancel out. It will carry the constant out from under the differential, cancel it here. And the first differential of x squared will be 2x dx. 2 in the denominator meets the 2 in the numerator. Everything is good. We have our original shape over here. What does it mean? That means that, and all this beautiful mess is, let me not step over here, it will be dv. You guys understand? dv. So what does that mean? It means that over here in general we have something that looks like e to the power of t, barring the multiplicative constant, basically dt equals basically again dv. So what is our function? Well, our function is, for the v, is this guy right here. So we write it down. V is equal to minus 1 over 2a e to the power minus ax squared. You see, normally when for example, these things happen, we do not get an elementary function. We need to introduce a non-elementary function. But luckily, the presence of x. And why is this x over here present? Because there are two copies, x squared. And where did the x squared come from? From the first derivative over here when we differentiate it. So already we see some cleverness. But again, remember our previous segment. What follows is not the mathematics, so to speak. The real grown-up mathematics was the process of experimenting, trying, failing, not giving up, and eventually converging on an interesting idea. The play of thought, the generation and regeneration, combination and recombination of ideas. That is mathematics. What follows here is not real mathematics, but for the most part, we need some computational wisdom. We need to be careful, but this is, I guess, in some sense, lesser mathematics. So now we know the shape of V, we know the shape of U. What happens over here? Exactly, U times V from 0 to positive infinity becomes what? Negative 1 over 2a plus x from here, we'll steal it from here, x times e to the power minus ax squared times sine of bx squared from 0 to positive infinity. Let me delineate this. So far so good. Everyone is on the same, we're all on the same page. Negative 1 over 2a from v, x from here, power of the exponent from here, the trigonometric function of sine from here, and the boundaries of integration from 0 to positive infinity. On the positive infinity, the sign remains bounded all over. The battle between the linear function and the exponential function is lost by the linear function. In other words, technically, we will say that the limit, the following limit of x over e to the power ax squared when x tends to positive infinity is a big fat 0 if we agree that a is greater than 0, which it is. This is one of the first limits that you will be studying in your first few weeks of the first semester of the first year in college in real analysis or calculus, whatever the name of your course will be in your country, but that is a basic real analysis limit. You should feel at home with its computation. That's how it works. So on the upper boundary of positive infinity, this term, this summand, vanishes due to the very aggressive behavior of the exponent, since a is strictly positive. So we'll write 0, negative, minus 0 on the lower boundary. The value of the trigonometric function of sine at 0 is 0, x at 0 is 0. Here x collapses into 1, so we have a double whammy. 0 times 0 is 0. So on both sides of integration, our uv term, u times v in this formula, vanishes. Now, because I have very limited amount of real estate, I will be erasing things often, but you guys keep good track on paper with the pen as we go along, so you should have no trouble manipulating these results in your records. Very good. During this short break, I erased all the materials that you guys now have on your record. You follow your records carefully. I just moved the definition of the function v, which we deduced in a public setting. I hope that everyone followed every step that we made. And also, if you have any questions, feel free to ask your questions in the comment section to this video. But I would like to note it one more time that the mathematics was the idea of orchestrate this whole computation that is about to unfold in this particular way. And what follows now is what happens after the mathematics walks out of the room, so to speak. The wonderful and almost a miraculous thing, or a side effect of all these observations, mathematics, not mathematics, is that what follows a sound mathematical idea will be a collection of very, in some sense, small and very straightforward steps that any sufficiently well prepared, let's say, high school student can carry through. In other words, nothing in the upcoming manipulations will be that difficult. Each and every step that we will carry out over here together with you in a public setting will be straightforward and easy to follow. So now we proved that the product u times v on both boundaries of integration 0 and positive infinity vanishes. We know the shape of u, we know the shape of v. Now we need to take care of this term. And what do? Let's carefully compute the first differential of u. What will it be? Well, again, it's a differential of a composite function that looks like a product of two functions over here. This guy vanishes. The first differential of x is just dx, so we write down the sine of bx squared plus, we know there will be a plus over here because the first derivative of the trigonometric function of sine is the trigonometric function of cosine. This function is composite. We know the rule for differentiating composite functions. The first derivative of the outer function times the first derivative of the inner function. The inner function over here is integrated carefully with respect to what? Here we differentiate with respect to x, not b, but x. So what will be the first differential of the second part of this function? Well, it will be 2x b times x, so it will be 2b x from this factor times x from the differential, so it will be x squared times, here all the products, what? Times the trigonometric function of cosine of bx squared, and all this stuff is terminated with the first differential dx. And now we simply take this differential, plug it into this formula over here, and we do not forget to multiply all this beautiful result through by negative 1 over 2a. Now let's carefully count the negative signs. In our first partial derivative of c with respect to b, what do we have in front? Exactly, we have one negative sign. Let's count 1. For the shape of the function v, we have the second negative sign. So 2 negative signs so far. But in this wonderful formula here, we have another minus sign. So minus times minus times minus is equivalent to minus 1 raised to an odd power, always comes out to negative 1 with the minus. So here we write down our result for the first derivative of c. Let me steal some green chalk over here so you guys can see that this is c, differential of c with respect to b will be. Now, this multiplicative factor is a constant. It does not depend on x at all, so we can carry it out from under the integral sign. What we will have? Minus 1 over 2a times the integral, this guy. And what do we have here? The integral from 0 to positive infinity of what? Well, the exponent e to the power minus ax squared times this usual suspect over here. This is sine, the trigonometric function of sine evaluated at bx squared dx. Isn't that wonderful? And then we also have what? The same function v times the second argument. 2 in the denominator collides with the 2 in the numerator collides with the 2 in the denominator. They cancel each other out. B goes upstairs. A lives downstairs. So what do we have? Minus B over A. And what integral remains over here? Well, let's carefully write this integrand down. Since this is the only material that we can factor out, and we already took care of this suspect over here, what remains? X squared times our exponent e to the power minus ax squared. Let me delineate this thing over here so we do not run into it. Times what? In the second summand over here. Times the trigonometric function of cosine times cosine. I apologize, this thing will be very tight. Bx squared dx. I'll say it one more time in words for you guys. Minus b over a of the integral from 0 to positive infinity. This is basically we're spelling out this term times v, right? V times du, so v times du, second term, x squared, a to the power minus ax squared times the trigonometric function of cosine evaluated at the argument bx squared dx. Now we go back to what we had before, and what do we see? What is the name for this summand right here? Which color did I use? The blue one. Let me use the blue one. Integral from 0 to positive infinity, e to the power minus ax squared sine bx squared dx is what? This is precisely our definition of the function s. So this suspect right here, let's designate him, is none other than s of a and b. So far so good. You guys agree? Very nice. And what is this integral right here? I'll carefully delineate him right here. Well, x squared times this horrible exponent times the cosine is what? Let's look at this guy. This is exactly this gentleman right here, or a lady if you will. Here, there you go. So this is our first derivative. Let me write it down like so. D of also s, the blue color, s, dB. So now what do we have? We have the multiplicative constant minus 1 over 2a in front of s, just like we claimed over here in this equation. And then we have negative b over a times what? The first derivative of the function s with respect to b, just as we claimed over here. So one more time, just to be good and polite mathematical citizens, let me do this. So it will be the result that we obtain over here is the first partial derivative of c with respect to the variable b will be negative 1 over 2a times s, this guy, minus b over a times what? Times the first partial derivative of s. I'll use the blue color. Here's the times. D, again, variable b. This is our result that we were aiming for. This is the result. This is precisely the claim that we made early, and in the next segment we will show how to construct a similar, but of course slightly different, a similar equation for the first partial derivative of the function s of a of b. If we were solving this problem in a seminar setting, then as a typical exercise left to the class to carry out on its own, this step we will normally skip, but for the benefit of all of our viewers, I'll provide you with the guidance how to construct the similar equation for the function s. Over here, we just go back to our definitions of the first derivative of the function c with respect to b and the first derivative of the function s with respect to be shown over here. And what do we see? What is the difference between the resultant integrals? Well, in the first derivative of the function c with respect to the variable b, what do we have? We have the trigonometric function of sine, and in the first derivative of the function s with respect to b, under the integral, we have the trigonometric function of cosine. But the remaining structure of whatever is left over, x squared times an exponent here and here, remains the same. Consequently, when we go back to a more closer encounter with the first derivative of the function s over b, shown over here, and apply the integration by parts to this integral here, once we partition this integrand over here in exactly the same way. In other words, here, based on this formula shown here, we again put u as a product of x times cosine this time. That's why I showed here in the red chalk, so that you guys can go back to your records and compare. In the previous segment, you have the trigonometric function of sine here, but since we're working with this integral, now we have the trigonometric function of cosine. The structure of the function v is the same. The product uv shown over here, evaluated at both boundaries, again vanishes. That much we all should understand why that happens, because this time the product of x times cosine times this exponent at the upper boundary of integration of positive infinity, here again the competition between the linear function and the exponent is quickly won by the exponent due to its aggressive rate of growth. The values of the trigonometric functions of cosine remain bounded at all times. And at 0 here, the exponent becomes 1, cosine becomes 1, but luckily we have x still present here in the first power. 0 kills the entire sum, and so 0 minus 0 is again 0. And we spell out the du shown over here carefully again. I showed the changes from the previous segment in the relevant places. Here in the first summand, we will have the trigonometric function of cosine shown in red, minus. In the previous segment, we had the plus over here, but now we have a minus because the first derivative of the trigonometric function of cosine is negative trigonometric function of sine. And here, this trigonometric function of sine is shown in yellow. But then the structure of the remaining term is the same, of bx squared times the first differential dx. Now, when we spell out the first partial derivative of the function s with respect to variable b, it's this guy. Applied the integration by parts to it once, and we continue writing over here. What do we have? We have this term times this term times the multiplicative constant. But now let us carefully count the negative signs again. No negative sign over here, one negative sign over here, one negative sign over here. So far it's two negative signs, they cancel each other. That's why we have the plus over here as shown. I showed the plus specifically in red color so you guys can see it. For the first summand associated with the cosine here and this guy, we have plus 1 over a times e to the power minus ax squared times cosine, this cosine right here, this usual suspect, of bx squared dx. Here, why do we have negative sign over here? For the second summand, remember, we took the first derivative of the trigonometric function of cosine. Flip the negative sign to negative over here. This sign came through to over here. Again, b over a. 2 in the denominator and 2 in the numerator cancel each other out, times the integral of x squared sine and the exponent. And now we go back and we decipher these integrals into the material that we have. The integral on your rightmost part is what? You need to be careful here. If you said the first derivative, that's not exactly true. It's the negative, the first partial derivative of the function c with respect to the variable b taken with a negative sign. You see we have a negative sign over here. So this is the negative first partial derivative of c over b. Plus we have a negative sign in front of it. So minus b over a times minus dc over db becomes a plus. That is why we have it over here. It became a plus. And here, the integral on your left is what? Well, this is our usual suspect that we introduced over here. This is our function c of a and of b shown over here. And to be good citizens, we write down one more time this formula. The first partial derivative of the function s over the variable b is 1 over 2a times c plus b over a times the first partial derivative of c over b. So now we have this formula shown over here. That's one equation, and we have the second equation over here. So far, so good. Again, guys, if you have any questions, feel free to put them in the comment section of this video. But in the next segment, I will erase the entire board because I will need all of it. And in the next segment, we will be solving precisely this system of equations. This equation coupled with this equation. If you know where this is going, you can skip the next segment and move on. But right now, I'll take a short break and prepare the board for the next segment. In the previous couple of segments, we constructed the system of equations that you see on the upper right hand side of your screen. And that system of equations contains the expressions for the first partial derivatives of the functions c and s with respect to the variable b in terms of the functions c and s themselves. Here our goal will be to solve this system of equations for the first partial derivatives of c and s with respect to b. Some of our viewers may feel at this point somewhat scared, maybe somewhat intimidated, but my advice to you guys is not to be scared, do not be scared, do not be intimidated, and in some sense, try to develop the attitude towards the mathematical material that is not that different from an attitude of a sculptor towards, for example, his or her clay. Here, of course, is not clay. This is a plastiline or a clay that never hardens. And let's say at some point I was interested in studying the structure of a human skull, and boom, here we go. I try to put a realistic rendering of a human skull. You guys can see it this way, that way, whatever which angle. And again, here we play games with this material that we have at hand, depending on what we want to do. We make, for example, the forehead a little narrower, the cheekbones a little higher. We make the nose, for example, going this way or that way. Press it here, push it here, make the cheeks maybe narrow, the chin larger, or whatever the case may be. And there we go. In season 1, episode 1, I showed you some of my other sculptures, and let's say at some point I was interested in the study of the structure of overall human skeleton, and boom, there we go. Clay, material that we have at hand, what we need to do, a study of a structure of the human skeleton. Here is a study of the structure of a human skeleton. There we go. Yet another case. I was interested, for example, in a more detailed study of a human foot, and boom, there we go. Material at hand, clay, a more detailed study of a human foot. And overall, the point that I'm trying to make is that we do not need to be scared of this here system of equations. This is a material, and what we want to do, we want to sculpt that material into what we need. And what do we need? Well, we need to express the first derivatives dc and ds with respect to the variable b in terms of the functions c and s themselves, and in a few short moments we will see why we need to do that. And in order to do that, again, precisely, we have the attitude of a sculptor, and we name, which colors did we use? For example, we name this guy X, and we name this guy Y, for example. So then, what would we have under this convention? Well, let's see. We will have, let's rewrite this equation. We will have X is equal to -1 over 2a s minus b over a y. You see, the partial derivatives disappeared. They got replaced with these symbols, x and y. And what do we have here on the bottom? We have y is equal to 1 over 2ac plus b over a x. You see, that maneuver should be understood by everyone. It's a simple mechanical replacement of the scary looking symbols with less scary looking symbols. We can handle those. Again, material that we have, the goal at hand, and this is how we do it. So what do we do here? Well, we have here the expression of x in terms of y, and on the bottom we have the expression of y in terms of x. So for example, you can proceed your own way here. I'll take this right-hand side of this equal sign and put it precisely over here like so. And then what will we have? Let's write it down here. X is equal to negative 1 over 2a s minus b over a of what? 1 over 2a c plus b over a x. You see, every step of the way in this case is quite simple, and it can be handled. In this case, this is really nothing beyond the proverbial middle school arithmetic, all courtesy a successful mathematical idea that we generated in the first place. So what we're witnessing now is what happens after mathematics with the capital room walks out of the room. So here we just keep rolling with this trivial arithmetic, and what do we have? We have negative 1 over 2as minus b over a times, let's keep this factor separate right now, over 2ac minus b and b, so here comes out squares, b squared a squared times x. What do we do now? We collect x's on the same side of the equal sign, so we carry this term, for example, over with the plus sign. So what do we have now? Here we have x times 1 plus b squared over a squared, and that is equal to negative 1 over 2a s minus b over a over 1 over 2a times c. Here on the left hand side of the equal sign, nothing scary going on. We just can simply spell out this expression over here. X times a squared plus b squared over a squared, parentheses, equals to this whole thing again, minus 1 over 2a times s minus b over a times 1 over 2ac. So far so good, that much we understand, nothing complicated. Now we agreed first that initially we'll take it that a is not 0, so we can here safely cancel one copy of a on the left hand side, cancel this copy of a, and cancel which one? Let's say this copy of a carefully. Now we express x in terms of the functions s and c. And what do we have? We have x is equal to a here from the denominator goes into the numerator. So here we'll have a over a squared plus b squared times, what do we have? We have negative 1 over 2 times s minus, again, we'll spell it out, a over a squared plus b squared times b over a times 1/2 times c. You see, no need to get fancy or complicated, quite straightforward middle school arithmetic. This copy of a and this copy of a cancel out, and what do we have? We have one and the same a squared plus b squared here and here. We have one and the same 1/2 and 1/2 over here. Isn't that wonderful? So now we bring everything back again under one denominator, and what do we have? X is equal to negative sign, and negative sign can be carried out the whole thing, negative sign. What do we have? A times s, so we write down a times s. Here, what is left over? B times c, wonderful, plus b times c over what? Over 2 times a squared plus b squared. So this is our result. We managed to express x. And what is x? Well, at the same time, we go back and decipher it this way. So this is our first partial derivatives of c with respect to the variable b. Isn't that wonderful? This is our result. Again, you guys keep good records on your paper, and I will erase a little bit over here and prepare the board for the expression of y, now that we know x, for the expression of y in terms of the functions c and s. And at the risk of sounding a little bit too annoying perhaps to some, we keep on sculpting. Here, once we know the shape of the function x in terms of the variables s and y, we simply insert the expression for x into the right hand side for y. I reserve the space for the answer over here, but let us unfold this middle school arithmetic together in this side of the board. So here we grab this expression shown over here and we go 1 over 2a times c plus b over a times what? X is given over here times, let me just do as visual candy, doesn't really mean anything, the square bracket, negative as plus bc over 2a squared plus b squared, just to collect everything into one place so that we can play some more middle school arithmetic games together over here. So now again, every step, as I promised, due to a fruitful mathematical idea that we generated earlier, and that was mathematics with a capital M. Now the consequences is every step is very straightforward, not that complicated. So what do we do here? Here we say that 1 over 2a times c, let's put c in the numerator. Here we need to generate what? A in this denominator and a in this denominator present, check. 2 in the denominator here and 2 in the denominator here, check. So what is the only missing link, so to speak, over here? The sum of squares, exactly. So the sum of squares goes over here, a squared plus b squared. What do we have here? Here we have minus b. So now here we have a b times s, or b times a times s, and negative minus b squared, b and b squared c, over what? 2a we already took care of, so that would be a squared plus b squared. Isn't that wonderful? So we keep rolling over here. What do we have? 1 over a times, let's see, spell it out, a squared c plus b squared c minus a b s minus b, let me delineate these guys here further so we don't get messed up, b squared c over 2 over a squared plus b squared. I'll show you these guys in a second what's going on over here. Simply we opened up the parentheses over here, nothing more, and we rewrote the denominator over here in such a way that 1 over a just factored out by itself, and 2 over a squared plus b squared is glued together for the reasons that we'll understand in a moment. But what do we see here? This b squared c and this b squared c cancel each other out. Would you agree? Bam, bam. So we continue here, come over here. What do we have? 1 over a times a squared c minus a times b times s. This is it. That's the end of the road for this guy. Over 2 times x squared plus b squared. What do we see again? Well, we see there are too many copies of a over here. It's getting crowded. 1 copy of a in the denominator, 1 copy of a over here, 1 copy of a over here. What is left? What is left standing is this, ac in the numerator, a times c, minus b times s, minus b times s, over 2 a square plus b square. Isn't that wonderful? And y, we remember we decide for y as the first partial derivative of the function s with respect to the variable b. I reserve some room over here. Let's simply move this result over here so we have everything in one place. So what do we have here? A times c minus b times s over 2a square plus b square. And all that is equal to, let's mark it carefully, ds over db. Now write this down in your records somewhere carefully. We'll work with this result further in the next segment, and also try to think on your own, if you were solving this problem this way, what would your next maneuver be? Maybe you will be able to come up with even more beautiful and elegant step over here, but one fruitful maneuver once we computed the first partial derivatives of our functions c and s is the following. We construct a function that takes a real number as an argument but produces a complex number on its output as follows. Let's call that function w, for example. W of b. B will be its independent argument, that is a real number. Remember, we introduced it early in our episode. And then we will say that that function is c plus I times s. And here the symbol I stands for the imaginary unit, which has the property that when squared it produces negative 1, and it is also one of two generators of the finite commutative multiplicative group of fourth roots of unity that looks like four numbers, plus minus 1 plus minus I, and exactly that symbol, the imaginary unit I, when it's raised to consecutive powers 0, 1, 2, and 3, that number generates precisely that multiplicative group of fourth roots of unity along with its conjugate image, which has its geometric interpretation as a point in the complex plane that is reflected with respect to the real axis. So the negative I also is another generator of the group. But anyway, here we construct this function over here, and now we will witness the awesome tactical powers of complex numbers as follows. Let us compute the first derivative of the function w. We'll start over here on this side of the board. dw over db over the independent variable b will be here. We have a little bit of a disconnect, admittedly, because here we will write the first partial derivatives of our functions c and s, and I hope that the mathematicians in the room will not be throwing hard and heavy and sharp objects at me over here, but here it looks like we have this dc over db plus I times ds over db. And now that we have the expressions for this first derivatives, we will say negative as plus bc over 2a square plus b square plus I times ac minus b times s over the same denominator, 2 times a square plus b square. Now, since we have two fractions, each of which has exactly the same denominator, let us rewrite this sum as one fraction, as a single fraction. What will we have? We will have minus a times s minus b times c plus a times c minus I times b times s over 1 in the same denominator, 2a square plus b squared. And now we concentrate our attention at the numerator of this fraction, and we wonder, is what we see over here is a chaotic pile of random symbols, or there is some structure to this set of symbols? Turns out there is some structure to it, and the structure here is the following. Let's take a look at the summands that have the factor of c here. This summand and this summand. Clearly we can factor this guy out. The function c can be factored out. So let us do that on this side of the board. Here we will write this is equal to what? I times a minus b. We'll prepare the factoring times c. The denominator will be one and the same. 2 times a squared plus b squared. And what will we have over here? Well, now we have two summands, each of which has the function s as its factor. So far so good. So if we factor s out, what will we have? We have to do that in a careful way, because if we just write s like so with some sign which we are to determine, then the product of s times minus b will be missing the imaginary unit I. So here we add the imaginary unit I times s. So if we multiply negative b times is taken with what sign? With the plus sign, then I times s times negative b will be negative b is, and this is this term right here. And now we just have to take care of this summand right here. When we have negative sign in front of the product as, what does that mean? Well, technically that's negative 1 times I times s. And what is negative 1? It's this guy right here. So in reality, what we have over here is I times s times I times a. I times I squared is negative 1, a s. Thus, if we factor these two parentheses out, then we will have exactly this expression shown in the numerator over here. Thus, the tactical advantage of introducing the functions c and s, constructing them into a complex valued function wb, taking the derivatives and then adding them together, precisely reveals that this is not just some random functions that have nothing to do with each other, but apparently they hide or lock in a certain structure. And what is that structure? Well, c plus is is exactly our function w, the way we constructed it. So what can we write over here in addition to that fact? Let me perhaps even designate it, let's say, with blue, so that you guys can see this is w. Now here, the factor of I in front of a can be taken out. And in this case, what will we have? A over 2. Here we will have a squared plus b squared. Instead of c plus is, we'll write w. So here we will have w. And what will we have in parentheses? Let's think about it. Here, a has the factor of I attached to it. We take this factor out. And then what will we have over here? We will have negative 1 over I. This negative 1 over I can be rewritten as negative 1 over I times 1. The 1 in this case, the number 1 plays the role of the multiplicative identity. This can be rewritten as negative 1 over I times I over I. This can be done because I is not 0. Then in this case, what will we have? Negative I over I squared. I squared is negative 1, so it will be negative I divided by negative 1, and this is precisely plus I. I will designate it with the plus sign just to make sure that we'll understand where it came from. So here we will write plus I times b. Isn't that wonderful? And now that we understand where this string of symbols, where did it come from, I will erase it to make room. But now let's think about it. What can you guys say about the sum of products of real numbers a and b? Is it just the sum of products of two real numbers, or there is some tactical advantage to deciphering this sum of products into a popular in complex analysis in general, a product of two conjugate complex numbers? This is, let's write it down here, let's spell it out, I over 2 times a plus ib over a plus ib times a minus ab times w. So this sum of products is really a product of two conjugate numbers, two numbers that are conjugate images of each other. A minus I times b is the conjugate image of a plus I times b, and conversely, a plus I times b is the conjugate image of a minus I times b. But now these two complex numbers cancel each other out, and what do we have? I over 2 times w over a minus I times b. And our long string of straightforward manipulations terminates with what observation? The first derivative of the function w over its independent variable b. We write that fact down over here. dw over db minus I over 2 times w over a minus I times b is equal to 0. Now, this number over here, the complex number a minus I times b, can be represented which way? Let me write it down maybe in yellow, somewhere in a discrete location, let's say over here. Let's put it down like so. A minus I times b is equal to square root of a minus I times b times square root of a minus I times b. That much should be understood. So this manipulation is similar to the manipulations that we would have carried out in the set of real numbers, but when we switch from real numbers to complex numbers, we have to be very careful with the function that is a square root of a complex number, because this is a multi-valued function. But we, out of all the possible branches of the square root of that number over here, we pick the branch where that root produces plus square root of a when b is equal to 0. I'll write it down for you guys later, but right now, what does that mean? That means that this equation over here, which we obtained simply by carrying this, the left-hand side of this expression, on the left-hand side of the equal sign, which we started over here, can be rewritten which way? dw over db minus I over 2 w here square root of a minus I times b square root of a minus ib equals to 0. And if we multiply this entire equation through by one copy of the square root, here in this summand, one copy of the square root will disappear, but one copy will show up over here, and what will we have? We will have dw over db times square root of a minus I times b minus I over 2 w over square root of a minus I times b equal to 0. In the next segment, we will work with this equation more closely. I will take a short break to erase all our manipulations and put this expression on the top of the board. And while I do that, you guys think, what do you see in this equation over here? What you are expected to see over here is a typical high school construct that is the first derivative of a product of certain two functions. That is, perhaps in high school you discovered, proved, or deduced on your own the fact that the first derivative of the product of two functions, u and v, with respect to an independent variable, let's say t, is equal to the first derivative of the function u with respect to t times v plus the function u times the first derivative of the function v with respect to t. And if we carefully look at this string of symbols, then we should immediately recognize what is going on over here. That is, in the Leibniz notation, we have the same thing that is written on the right hand side of the board that you see over there using the Lagrange notation. That is, u is w, v is square root of a minus I times b. And what is the independent variable t? The role of the independent variable t in the formula over here is played by the symbol b. And what do we have encoded in this first sum over here? Well, exactly. The first derivative of the function w with respect to the variable b times the square root of a minus I times b plus what? U or w times precisely what? The first derivative of the square root of a minus I times b over the variable b. And just to make sure, obviously, if you are in the mathematics that far and if you're taking on this type of problems, of course you need to be at home with all of this information, but just to make sure that we're all on the same page, if we decipher this, in general, you remember that the first derivative of the function of square root, again with respect to x, will be what? The derivative of x raised to the power 1/2, then 1/2 goes down, 1/2 times x to the power 1/2 minus 1 equals 1/2 over x to the power minus 1/2, which is the same as 1/2 times 1 over square root of x. Here, the role of the independent and our favorite variable x is played by the symbol b, but that symbol b is not just by itself. It is entered into this function with the factor negative I in front of it. So here, as the first derivative of the composite function, we take the first derivative of the outer function times the first derivative of the inner function, which is this. And if we multiply this result over here by the first derivative of negative I b, we will get precisely negative I over 2. This is our result. And what do we have altogether? We have it that in the Leibniz notation, d per db, d over db of w times square root of a minus I times b is equal to 0. And this is perhaps one of the simpler differential equations. The first derivative of something is equal to 0. What does that mean? It means that that something is a constant. So we write w times square root of a minus I times b is a constant. And how do we recover the value of this constant? Well, because w is a function of the independent variable b, In order to recover the value of the constant k, we need to play with the variable b and set it to an advantageous value. While I'll be taking a short break and erasing the board, preparing it for the next segment, you can take this time to think on your own, what should we set the value of b to in our function w of b in order to recover the value of the constant k. Of course, one advantageous value of the parameter b, which will allow us to compute the name of the constant k in a straightforward manner, is 0. In other words, in order to compute the value of the constant k, we put b is equal to 0 all around over here. Consequently, on the one hand, for the function w of 0, we have what? W of 0 equals c of a 0 plus I s of a 0. This integral over here, we remember, contains the integrand of this integral contains the factor of sine of bx squared, which means that when b is 0, this integral vanishes. And in this integral, we have under the integral sign the factor of cosine of bx squared. When b is 0, cosine of 0 is 1. So what do we have? We have over here the integral from 0 to positive infinity e to the power minus ax squared dx, and we agreed that we know the value of this so-called Euler-Poisson integral, and that value is 1/2 square root of pi over a, where a is strictly greater than 0. That's on the one hand. And on the other hand, over here, what do we have? Well, technically we have w of 0 times square root of a minus I times 0 equals k. Would you agree? This is the case where we put b equal to 0 in this string of manipulations. For the value of w of 0, we have 1/2 square root of pi over a times I times 0 is 0, square root of a equals 2k. And what do we witness? Square root of a, square root of a cancel each other out. And what do we have? Now we know the name of the real number that is a constant in this expression. That is square root of pi over 2. Game over. Now we know, let me write it down over here, w of b times square root of a minus I times b is equal to square root of pi over 2. And what does that mean? That means that we know precisely the shape of the function wb. And again, while I'll take a short break to erase this string of manipulations to prepare the board for the next segment, you think on your own, how would you express, or in which form, in which shape would you write the function w of b on your own, and compare your ideas to my result. Now that we know all the ingredients that go into cooking up our function w of b, let us bring it home and see what it will actually look like. Here, I wrote down the expression that we obtained in the previous segments. Our function w of b times the square root of a minus I times b is equal to square root of pi over 2. And now all we have to do is isolate the function w all the way by itself, let's say on the left-hand side of the equal sign. And how do we do that? Well, exactly. We rewrite this equality shown over here as follows. Square root of pi over 2 times 1 over square root of a minus I times b. In other words, in the grown-up mathematics speak, we multiplied both sides of this equation by the inverse of the square root shown over here and obtain this expression. But now we want to get rid of the imaginary unit I in the denominator of this ratio. And what do we do here? Here we execute our favorite maneuver of multiplying both sides of the fraction by which number? By square root of a plus I times b, by the conjugate image of this complex number. So what we have in the numerator is a plus I times b over square root of a minus I times b times square root of a plus I times b. Here we have to be careful. When we merge these two expressions, we get the product of two conjugate numbers, and that means that what we have here is square root of pi over 2 times square root of a plus I times b over square root of sum of squares, a square plus b square. Here, just to make sure that we understand where that result came from, a minus I times b times a plus I times b equals precisely a square minus the square of the second term. I square is -1. -1 times -1 is +1. A square plus b square. And now let's write down the official result. From here we have for our function w of b is a multiplicative constant, square root of pi over 2 times 1 over square root of a squared plus b squared, like so, times a square root of a plus I times b. And again, this is a standard maneuver in complex analysis. It turns out that magically it is possible to decompose or to decay, if you will, this expression again into a sum of two pieces shown over here that have exactly the same shape, where one piece looks like a function in the variables a and b plus another piece that looks like I times another function in the variables ab. That maneuver over here is standard in complex analysis, and because we know overall that's how we defined our function w(is), once we recover the shape of the helper function g of a and b and h of a and b, we can consequently equate the real parts and equate the imaginary parts, and voila, we will know how to spell out the integrals c and s. So the only question over here remains, tactically, that's the only obstacle that remains, we're pretty much done, is how to manipulate or how to submit the square root of a complex number shown over here into the shape shown over here. Those of our viewers who know how to do that and how to proceed correctly on their own can skip the next segment, but for the benefit of those who do not know how to maneuver the square root shown over here into expression shown over here, I will explain that in the next segment. Wonderful, this segment is optional. This is only for those who have trouble deciphering the spelling of the square root of a complex number in terms of the ingredients that sit under the square root, and submitting that square root to the shape that looks as follows: a function in the variables a and b plus I times another function in the variables a and b. And the way we do that is a pretty much standard maneuver when we study complex numbers or in a slightly more grown-up setting in complex analysis, and that is the following. Here we assume that the square root of this complex number can be represented as yet another complex number. And we do that, we realize that assumption by writing the following string of symbols. A plus I times B is equal to X plus I Y. And here the shape of X and Y in terms of A and B is precisely to be recovered from where? Well, in a way we feed for the search for the values of X and Y in terms of values of A and B on itself, on that expression over here. We square both sides of it, and what do we have? A plus I times B is equal to X squared minus Y squared plus I times 2X Y. Remember that I squared over here is -1. So we group in this result the real part and we equate it to real part. And then we equate the imaginary part. Let me designate it with double, with the imaginary part. And what do we have? We have A is equal to X squared minus Y squared, and B is equal to 2 times X times Y. And here again, one more time. The square root of a complex number is a multi-valued function, but out of all the possible branches of that function, we pick such a branch that when b is equal to 0, our function yields plus square root of a if b is equal to 0. If b is equal to 0, this is our choice. This is how we choose to select a particular branch of the square root of a complex number function. And we also know, remember, we have another helper tactical observation that we will use in a few moments, that b is what? B is strictly, b is ideally is greater than 0. And if b is greater than 0, that means that these two guys, x and y, change in unison. Either x and y are both positive or x and y are both negative. But this observation over here, that we choose the branch of the square root in such a way that we obtain plus square root of a if b is set to 0, will actually lock in only positive x's and only positive y's in a moment. So from this, let me actually, which way? Well, yeah, let's go this way. So from this relation, we deduce, for example, this expression in some sense is symmetrical in x and y, and here is also, we can work either way. Let's say I work with the y. From here we express y equals b over 2x, and now we put this over here, and what do we have? A is equal to x squared minus b squared over 4x squared. That maneuver is understood by everyone. And what do we have now? Now we have an equation that is biquadratic in x. How do we obtain that information? Well, we multiply both sides of this equation by, let's say, x squared. We multiply both sides. What do we have? Then x to the 4th minus ax squared minus, what over here do we have? X squared and x squared cancel out. We have b squared over 4 equal to 0. So this equation is mercifully biquadratic in x. In other words, we can put x squared as another variable, z or t or whatever your favorite symbol will be, but hopefully at this point we all know how to spell out the roots of this equation. Remember the highbrow theory of groups information that we now possess, and which tells us that we can spell out, as long as the equation over here in general is not of degree 5, this polynomial equation, we can spell out the roots of such an equation ahead of time using nothing but a finite combination of addition, subtraction, multiplication, division, and extraction of square roots for this guy. And for, in this case, let me separate this a little bit like so. we will write down the result right away, because this will be result for x squared. We take two square roots again, plus minus square root of what? For the quadratic equation, we will have minus times minus a. So that will be a plus, I'll explain why we're taking plus in a moment, square root of a squared minus b squared over 4 with a negative sign times 4. So that will be a squared plus b squared divided by what? Divided by 2. Here is 1, so divided by 2. And now to address the question, ideally, you know that in high school you're told, or in middle school you're told to take plus or minus for two roots. That is exactly the thing. But in our case, remember, we're choosing such a branch of the complex, of the square root of the complex number function that yields plus positive a, square root of a, if b is 0. So here, precisely that, if b is 0, the square root of a squared must be taken with the plus sign according to our choice. So there is only one sign over here. And this is our answer for x. Now that we know x, do we know y? Yes, we do. Again, you can skip this if you know how to handle the rest correctly and on your own. But here we simply take the value of x over here and insert it into the right hand side of this equation. What do we have? B over 2 plus minus, let's not forget plus minus, b over 2, and then what will it be? It will be square root of 2. Here we have a plus square root of a squared plus b squared. There is no magic over here. There is a product over here. We simply took this expression for x, inserted over here, or multiplied the fraction b over 2 by the reciprocal of x. This is what we have. Turn this guy upside down, so to speak. And now what do we do over here again? Well, by now this is our favorite maneuver. We multiply the denominator and the numerator by the conjugate image of what we have in the denominator, or by a minus square root of this thing. And what do we have? Let me spell it out again. Let's be polite and spell this out. So we have 2 times a minus square root of a squared plus b squared divided by a plus square root of a squared plus b squared times a minus square root of a squared plus b squared. And we'll continue on the left hand side of the board, but that maneuver should be understood by everyone. We simply took this fraction and multiplied the denominator and the numerator of that fraction by the conjugate image of what's in the denominator. And in this case, the conjugate image of the denominator is simply a minus the square root, as shown over here. And now what do we have? Let's continue over here. Plus minus b over 2 square root of what? Here we have 2. We'll multiply it by something in a second. What do we have in the denominator over here? Well, we have something plus something times something minus the same something. So that would be what? A difference of squares. So in the numerator we have a squared minus the square of the square root. So it will be minus square root minus b squared. And what do we have on top? Let us carefully think. A squared and a squared over here cancel each other out. Negative b squared, we steal one negative 1 in the denominator, insert it into the numerator, and what do we have? Minus a plus square root of sum of squares. A squared plus b squared. And That is all if we move this guy over here. So this becomes a plus. If this becomes a plus, then square root of b squared, again, we take it as b. B and b cancel each other out. So this and this cancel each other out. And once we move 2 under the square root, like so, it becomes 4. One copy of 2 cancel out with this one. And what do we have in the end? Plus or minus square root of negative a plus square root of a squared plus b squared over what? Over 2. Now this is our expression for x. For y. Let me write it down over here. So this is y, this is x, but again, because our expression for the product of x and y must be equal to b, which is greater than 0, 2 is greater than 0, it means these two parameters change their sign, changes in unison. If x is positive, y is positive. If x is negative, y is negative. But here, if b is 0, then what do we have? Square root of a squared is a plus a, 2a over 2 is a. Square root of a must be what? We need to take the positive root. So in general, our answer is that out of 2 roots, we pick this one, the one with the plus sign. And if x is positive, then according to this inequality, x times y must be greater than 0 and x is positive, then y must be positive as well. So here we pick also the plus sign. And pretty much we are done. Let me take a short break, erase all the intermediate material and prepare the board for our final segment. Lastly, now that we all understand where did this particular spelling of the square root of the complex number that we deduced in the previous segments come from, we can finish the solution of this problem. That is, we previously have shown that this square root of the complex number a plus I times b can be expressed as follows. Let me continue writing on the left-hand side of the board. And thus we have square root of pi over 2 times I1 over square root of a squared plus b squared times square root of a plus square root of a squared plus b squared over 2 plus I times the same multiplicative constant square root of pi over 2 times 1 over square root of a squared plus b squared times square root of minus I plus square root of a squared plus b squared over 2. And precisely because we have two different expressions for one and the same mathematical object, the complex valued function w of b that takes as its input a real number b in two different ways, as c plus is, and then as this expression plus I times this expression, then, because this is how these things work in complex analysis in general, that means that the corresponding real parts, or this part and this part, are equal. And that means that the expression shown over here stands for the function c. And the corresponding imaginary parts, this part and this part and this part over here, must be one and the same. So this expression here stands for the function s. And consequently, once we understand that, let me take a very short break and erase this line, because I will need the entire space. I'll perhaps probably even erase the top line also. I'll need the entire board for this final segment, but we all understand where did the expressions for the integrals c and s that I'm about to write in the next segment, where did these expressions come from? And now we simply take our square roots of the sum of squares, a squared plus b squared, that we obtained for the expressions of x and y in the previous segment, and merge them with the square root that we had as the factor on the right side, and obtain the following expressions for our integrals c of a and of b as follows. Integral from 0 to positive infinity e to the power minus ax squared cosine of bx squared dx will be 1/2 of the square root of pi over 2 times, here we merge all the square roots into one big happy family, a plus square root of a squared plus b squared, like so, over a squared plus b squared, under the assumption that ab is greater than 0. And we have a similar expression for the function s of a and b as the integral from 0 to positive infinity e to the power minus ax squared, the trigonometric function of sine, this time sine of b x squared dx as a similar thing, 1/2 over square root of pi over 2 times square root of negative I plus square root of a squared plus b squared, like so, over the sum of squares. Don't forget that we carried this sum of squares from the same square root in the denominator under the assumption ab is equal to 0. These are two intermediate results, and again, remember that we obtain these results without doing any integration per se. And if you're writing such a material for publication or for a professional review, you have to show that the integrals s of a and b and c of a and b represent functions with respect to the parameter a that are continuous over a, and that is why, and that can be shown by using the corresponding uniform convergence of the integrals in hand. And if we take the limits, let's say we take the limit of the function c of a and b when a tends to 0 from the right, then what will we have? We will have the integral from 0 to positive infinity of cosine of bx squared dx. And now let us carefully write down this expression: 1 over 2 times square root of pi over 2 what? A is 0, a is 0, a is 0. Square root of b squared is b. This is just b squared. B over b squared cancel out. We have one copy of b in the denominator over 2b. And then b is greater than 0. 2b or not 2b? The answer is, of course, 2b. And for the limit of the function s of a and b when a tends to 0 from the right, we have our integral from 0 to positive infinity of the trigonometric function of sine of bx squared dx, which is 1 over 2 times square root of pi over 2. Well, in this case, note that because a vanishes and becomes 0, the fact that it's taken here with the minus sound doesn't really matter. Again, a is 0, square root of b squared is b. A is 0, b over b squared. One copy of b in the numerator and denominator each cancel out. We have 1 over b. So here this b migrates under this square root like so. Again, b is greater than 0. And what do we see over here in this limit? In this limit, we of course recognize our Fresnel integrals, where the parameter b is set to precisely 1. So if, let's say, I erase it, we understand that this is our constraint. This is our constraint. Let me probably write it down maybe over here on top. B is greater than 0. Here is the same deal. B is greater than 0 because we're dividing by b. So the original problem that we were asked to solve in S2M22 is to recover the value of the Fresnel integrals over the positive branch of the real axis. This can be done when the value of the parameter b is set to 1. And what do we have? Let me separate this a little bit like so. For the integral from 0 to positive infinity of cosine of x squared dx, we have 1/2 times square root of pi over 2. For the integral from 0 to positive infinity of sine of x squared dx, we have the same result, 1/2 times square root of pi over 2. We're pretty much done, and if you allow me to take a few seconds of your time, recall that, let me use maybe the blue chalk, perhaps in middle school, perhaps sometime in high school, you learned about the following trigonometric identity. Which way do you guys write it usually? You probably write it cosine squared of x plus sine squared of x equal to 1. This identity holds for all real numbers x, for all x real. In words, the square of the cosine of x plus the square of the sine of x, the trigonometric functions, is 1. And again, this is the joke. Now you have a similar identity, which says that, let's write it down, the integral from 0 to positive infinity of cosine, but this time x squared dx, plus the integral from 0 to positive infinity of sine of x squared dx is equal to precisely the square root of pi over 2. Again, this is a joke because here we're taking cosine of x squared integrals. It's much more complicated mathematical objects, but just to keep the light mood and do not take yourself too seriously, here is the joke. And again, I probably and most likely do not say these words too often, but it doesn't mean that you should not do it. At the end of every problem-solving experience, it is a good idea for you to go back and partition all your results, all your experience, into two more or less kind of sort of neat piles: mathematics, not mathematics. In this particular problem, what was the mathematics and what was not mathematics? In this particular problem, the mathematics in the grown-up sense was the process of generating the idea of deciding to evaluate our favorite Fresnel integrals using precisely the equation problem-solving approach. Introduce as many variables as needed, construct as many equations as possible, balance the quantity and the quality of the equations against the specific nature of the problem, solve as many equations as you can, validate the results against the original problem. You know the program, and this is precisely what happened over here. Note also well that as a side effect of a successful mathematical idea, each and every step that followed that idea once the mathematics, so to speak, walked out of the room was pretty much straightforward. And we all saw how these steps unfold in the public setting, which is to say that in mathematics there are no secrets, but there are plenty of mysteries. This is it for the problem S2M22, and we will move to the next challenge in the next segment. With this episode, we conclude our dedicated and initial study of the equation problem solving approach, but that does not mean that we will not use it again. Quite the opposite. So far, we have covered the following problem solving approaches: transform and conquer, reinterpret and conquer, reverse order, space-time, and equation. And in the previous problem that we just solved, the problem S2M22, where we managed to evaluate the Fresnel integrals over the positive branch of the x-axis via the equation problem solving approach, we actually used which of the approaches that we studied? Exactly, we used the reverse order problem solving approach here and there. Remember how we took the unwieldy and chaotic looking string of symbols and folded that finite sum into a product of two factors, and then we also took an expression that looked like a pile of symbols, but then in reality that turned out to be a derivative of a specific function, a product of two functions, w and the square root. So that means that, again, once in the moment we learn about a new problem solving approach, such as the equation, for example, problem solving approach, we immediately or instantly or right away incorporate it into the process of solving the next problem. And just because we're not studying, for example, the previously covered problem solving approaches in the study of the current one does not mean that we cannot use the previously studied approaches. Quite the opposite, we should. And that is how we develop the feel and a better understanding for these approaches. Also, that's one thing. The other thing, the idea of an equation also sits at the foundation of the grown-up mathematical layers, such as the theory of differential equations, the theory of integral equations, the entire massive body of the equations of mathematical physics, and in some sense, the entire universe of theoretical physics rides on the notion of an equation. So it's a good idea to understand how equations of different types generally work. Starting from the next episode, we'll begin a dedicated study of the problem-solving approach that I call reduce and conquer. Again, all these names are completely arbitrary. They are mine, so to speak. If you think that you can come up with a better name, by all means, be my guest. And I will use the mathematical problem S2M23 as the fodder to explain how the reduce and conquer problem solving approach works. If you can figure out that on your own, good for you. Share your experience with us in the comments to the next or this video. But the challenge in the mathematical problem S2M23 is the following. In base 10, we will not be jumping around bases. So to be for deterministic purposes and to be completely clear and explicit about it, in base 10, how many 5-digit perfect squares such that if 1 is added to each digit of such a square, then a perfect square results are there. In other words, let's say we have a 5-digit number that is a perfect square. We take that number, add 1 to each digit, and as a result of adding 1 to each digit in this 5-digit perfect square, we obtain yet another perfect square. How many such 5-digit numbers are there? What do you think? Again, remember, on this channel, we do not really care that much about the answer itself. If you come over to me and say, Roman, blah, the answer is this, the reaction will be, so what? We care way more about how that answer was obtained. And why? Because remember, mathematics, first of all, is an art of telling a story, is an art of telling a story of how and why, and it is precisely that story of how and why is what we want to hear. That story is the first-class citizen on this channel, and we want to know how and why the answer to that specific problem is what it is. Thank you very much for your time. Thank you for watching. I will see you in the next episode, in which I will share my solution of the mathematical problem S2M23.